Hello everyone, my name is Alex Hintz. I am a Bridge Program Fellow with the EIA Eswatini program, and today I'm going to walk you through how to interpret the data that we provide in the soil classification chart in the technical survey forms, how to use that data to estimate allowable bearing capacities for your soil for your sites. So before I begin, just a recap of what we talked about in the previous video. We discussed everything related to filling out this chart in the field. We talked about what the visual classification is and how to use that. We talked about what the toughness test classification is and how we perform that test, and then also the 13 millimeter rebar penetration and those characteristics we talked about. But we left off before we estimated bearing capacities for the soil. So that is what we will discuss in this video today. And moving on now to show you the appendix in the same uh, technical survey form. This is just page 5 of that form, which we provide to you. You'll notice that we have two different charts here. One is for fine-grained soils, and one is for granular soils. And again, granular and coarse-grained soils, those are the same thing. That's just a different way of saying it. And you may see it written differently in between different countries or different textbooks, but granular and coarse-grained soils are one and the same. And again, these roughly follow the unified soil classification system for determining or for classifying soil based on the grain size distribution. So that just means we classify the soil based on how much of it is comprised of small particles and how much of it is comprised of larger particles. But you can look into that more on your own, the Unified Soil Classification System, if you're interested. For now, we will just move forward, knowing that fine-grained soils and granular soils are determined based on these two columns in the chart. So let's walk through the first example. But actually, before we walk through that first example, I do want to explain what the tables are for and walk through what the content of these tables is. So for the fine-grained soils, for this table, we can see that we're going to be looking at the allowable bearing capacity column. This is going to be important. The half-inch rebar test column, this will also be important. And by the way, half-inch and 13 millimeters are the same, just US and metric units. And then we're also going to look at the penetration characteristics in this chart. So using all of these three things combined, we can arrive at estimating a range for the bearing capacity for your soils. Looking at the granular soil chart, we can see that here we'll be looking at this column for the allowable bearing capacity. We can also look at friction angles for granular soils, and we're going to focus on the penetration characteristics here in this chart. You'll notice that there's not a half-inch rebar test column, so we don't have um, depth of penetration related to specific bearing pressures for granular soils, but that's okay because we have still a range and a description of the of how difficult it was to penetrate by hand or by hammer, and we'll use the data on the form the previous chart to come up with a range for the bearing capacity. So a couple things to note here. The first thing I want to point out is that the allowable bearing capacities are already factored, meaning you do not need to apply a factor of safety to the numbers that you assign based on these ranges for bearing pressures. If you did assign a factor of safety and divided by 1.5 or 2 or whatever, that would be overly conservative and redundant, and we don't need to do that. So these are already factored, so move forward with confidence, knowing that the range that you select here will be a conservative assumption. There are already conservative estimates built into these ranges. And another thing to note is that the half-inch rebar test here, these depth depths of penetration, 10, 5, 4, and 1, these are these were achieved by hand penetration. They were not hammered using the 5-pound mallet. They were pushed by hand. And these are equated with specific values here based on field research conducted by some engineers who have worked on these bridges before, and so they have experience in testing what the soil capacity or the bearing capacity of the soil is. So for our purposes here, this chart will suffice, and it will be a good exercise going through to assign those bearing pressures. One last thing to mention on the appendix is this table down here, the EIA Standard Soil Properties. This is a reference for you to use, which simply states these are the standard soil properties that EIA uses for any given bridge site here in Eswatini. We typically assume a friction angle of about 30 degrees, unit weight of 1800, and allowable bearing pressure of 143 kilopascals. And 143 kilopascals equates to 3,000 pounds per square foot of bearing pressure. So use these two tables to come up with bearing pressures to assign your soils, but also keep in mind the standard soil properties that we use. I would uh, I would say that these are a valuable resource in case you're not sure and in case you're kind of stuck on whether which direction to go in terms of assigning bearing pressures. You can always refer to this table here to get an idea of what we typically assign. And these numbers will be pretty conservative and pretty safe to assume for most bridge sites. But let's go ahead and jump in now and go through a couple of examples. So you'll see for soil sample number 2, again, because we achieved the 1/8 inch logs, we know that it's a fine grained soil. Because it's fine grained, I'm only going to be focusing on this first chart here, the fine soils chart. And looking at this is see that 10 inches was achieved by hammer and 2 inches was achieved by hand. So let's go to the chart again and see that since I was able to achieve 2 inches just by pushing the rod with my hands, that I can look here and see that I'm going to be somewhere in between the 1 and 4 inch range. And that means that I'm going to be somewhere in between 2000 PSF and 3500 PSF. Now, using simple interpolation and just a linear assumption of that, I can say with confidence that for 2 inches of penetration by hand using a half-inch rebar, that I can achieve 3,000 pounds per square foot of allowable bearing capacity for this soil. And again, that just comes from looking at the depth of penetration, whether it was by hand or by hammer, and then coming to this table here and seeing that the half-inch rebar test, again, 4 inches equates to 2,000, 1 inch equates to 3,500, so I know I'm somewhere in between that range, and I can assume 3,000 using linear interpolation. Now, let's say, for instance, I didn't have this second uh, item here for the 2 inches of penetration by hand. If I only had 10 inches by hammer, then I could still assume a bearing pressure, but I would have to look at the penetration characteristics here and try to equate these with the rebar penetration by using the hammer and the 25 strikes to the hammer. So in most cases, the penetration by hand is going to be pretty difficult, we found in the soils here. So for a lot of cases, we were only able to achieve any penetration at all by using a hammer and striking it. So in those cases, you would come back to this table and look at the penetration characteristics here. And you'll notice that this table only goes up to 3,000 PSF. in terms of um, allowable bearing capacity and for fine-grained soils. So I wouldn't assume anything higher than that, and I would be uh, very confident if you do assign 3000 PSF. Just make sure that you can justify uh, your reasoning for this. Otherwise, fine-grained soils typically are weaker, and so 3000 is the upper limit for these soils. So moving now to the third soil sample, we'll see that it was gravelly sand and that we did not achieve the 1/8 inch logs. So this confirms that it is a coarse-grained or granular soil, which means that I'm going to be focusing on this chart here for granular soils. Now, coming back to the data that we collected in the field, we'll see that for 2.5 inches of penetration with a 5-pound hammer, there was a high degree of difficulty used to achieve that, and there were 25 blows to the hammer to achieve that. So, using that information, now I'll come to this chart here. And I'll read through these characteristics and explain what they mean broadly. So, penetrated by rebar by hand with easy effort. That's not us because we had to use the hammer. So we're going to be a little bit stronger than this first uh, this first classifier of the soil. The next one, for loose soil, penetrated by 13 millimeter rebar by hand with difficult effort. Again, uh, this is not what we achieved. We had to use the hammer for that. We couldn't achieve anything by hand. So we know that we're not in this loose category either. Now moving to the next one, penetrated by rebar with a 5-pound hammer, medium effort. Okay, we should stop here and consider we did penetrate using the 5-pound hammer, but I said difficult effort instead of medium effort. Now, or I said high instead of medium. Now, these are obviously subjective terms based on who is conducting the survey and who is striking the rebar with the hammer. So one could argue that I would fall into this range, somewhere in between 2,000 and 4,000, because, again, I penetrated using the hammer, but difficult effort. But here it's stated medium effort. So for this one, the range of the medium soil goes from 2,000 to 4,000. Now, I would not recommend anyone assigning bearing pressures greater than 4,000 PSF, just because it's very unlikely that the soil um, is that strong in our cases. It's just sometimes we're building on farmlands. Sometimes there's a river nearby, so all those things affect the strength of the soil. So assuming something higher than 4,000 is not is not recommended practice to do, and definitely not going above 8,000 for this chart. So for this chart, we can essentially stop looking at the dense and very dense, but just stop right with the medium density soils because we're probably not going to be seeing anything higher than that. And honestly, you're probably not going to need a soil much stronger than 4,000 PSF in your bridge design. So for this one, 2.5 inches, high difficulty. I'm going to say that this is towards the upper range of this 2,000 to 4,000 because I said it's high effort instead of medium. So that would mean it's more dense than the average of this range right here. So because of that, I think that I can safely assume and confidently say that I can achieve 4,000 PSF. And again, this would be the upper limit, and I'm only assigning this 4,000 PSF because there is a high degree of difficulty and there is minimal penetration into the soil. So I can say that I'm probably near the upper part of this range. And as far as friction angle goes, 36 is also a very high estimate. Typically, we don't see soils with anything higher than 36 in just their natural state. So I would be weary of going up to 36. I may say 35. You might be comfortable with saying 34. Again, the EIA standard is 30 degrees, but we can at least be 32 safely, but somewhere in between that 32 and 36 range for the friction angle. And the last example we'll see quickly is the silty sand, and this one was confirmed to be coarse grained or granular. And for this one, we achieved 8 inches using the hammer with, again, a high degree of difficulty. So going back to this chart, we'll find ourselves somewhere in this medium range again, between 2,000 and 4,000 PSF. And this is going to just require some judgment and some justification and some reasoning to figure out what an acceptable bearing capacity could be for this one. But because I know it's not quite as dense as the sample number 3, I know that I'm not going to be 4,000. I'm going to be something less than 4,000. But it is still a fairly dense soil, only achieving 8 inches of penetration with a high degree of difficulty. So I think that I can assume that it's going to be more than the EIA standard soil property of 3,000 PSF, but I don't want to go too much higher than that without any further um, analysis or justification. So I know that I'm going to be less than 4,000, but I can also reasonably say that it's a very dense soil and I can, or it's a relatively dense soil and I can go a little bit higher than that 3,000 number. So for this one, I'm going to say that it's 3,250 PSF for this bearing capacity. And again, that's simply based on I was somewhere in between this 2,000, 4,000 limit because I found myself with this characteristic being the closest description to what was achieved in the field. And based on that, I know that I'm not quite at 4,000 because my other sample was at 4,000 and this one is weaker. And I think that I can be a little bit higher than the allowable bearing pressure that we typically use in just a standard assumption. And again, anywhere in between this 2,000 and 4,000 range would be acceptable to choose. And for friction angle, again, you could choose something in between the 32 and 36 degree range, but whatever it is, it would probably be lower than whatever friction angle I assume for the sample number 3, because again, it is a weaker soil because um, the depth of penetration was greater with the same difficulty and same number of hammer strikes. So I hope that helps in walking through how to interpret this data and use it to estimate allowable bearing capacity. Remember, for all of your bearing capacities that you're going to assign, that it is based on engineering judgment, and so you do need to just employ some critical thinking and reasoning and be able to justify your answers about why you chose bearing capacities and why you didn't choose some bearing capacities. So yeah, I hope that helps. And reach out to the EIA staff if you have questions about your soil in particular. If there's things that we can clarify regarding this chart here, reach out to us and we'll help clarify to help guide you in the right direction for estimating your bearing capacity for your soil. So hope that helps and have a good day.